Hello children, let us understand work done by a force. We will consider four scenarios: when force is constant, when force is variable, when force and velocity are perpendicular to each other, and when force is spring force. Scenario 1: when force is constant. We know that work done W is equal to integration of F dot dr. If F is constant, it can be taken out. So W is equal to F dot integration of dr, and integration of dr is equal to R. So W is equal to F dot R. Suppose force and displacement vectors make an angle theta with each other, then work done W is equal to Fr cos theta. We will consider three cases here. When theta is equal to 0 degrees, that means force and displacement vectors are in same direction. Then W is equal to Fr cos 0. Cos 0 is equal to 1. So W is equal to Fr. Work done is maximum in this case. When theta is equal to 90 degrees, that means force and displacement vectors are perpendicular to each other. Then W is equal to Fr cos 90. Value of cos 90 is equal to 0. So work done is 0 in this case. When theta is equal to 180 degrees, that means force and displacement vectors are opposite to each other. Then W is equal to minus Fr. That means work done is negative in this case. Consider a particle is moving along the straight line AB. Its mass is m and velocity is v. Force acting on it is gravitational force that works vertically downwards. Its component along the velocity or displacement is F cos theta. So work done by this force from point A to B is given by F cos theta into AB. This can be written as F into AB cos theta. F is equal to mg. In this right angle triangle ABC, AC is equal to AB cos theta and AC is equal to H. So in place of AB cos theta, we can write H. So work done in this case is, let's say, W1. So W1 is equal to mgh. Now consider the same particle is moving along the curve AQB. It is at Q. For a very small displacement dr, draw perpendiculars on AB. Let's say width of this strip is dx on AB. For a very small displacement, we can approximate this to be a rectangle so that dr is equal to dx. Work done in this case is given by W2 is equal to integration of F dot dr from Ri to Rf. Since f is constant, so it can be taken out. So W2 is equal to F dot integration of dx from A to B. And integration of dx from A to B is AB. So W2 is equal to F dot AB. And F dot AB is equal to F into AB cos theta. AB cos theta is equal to H. So W2 is equal to mgh. We notice that work done is same in both the cases. Now consider the particle is traveling back from B to A. So in similar way, we can prove that work done in that case will be minus mgh. Now we will draw two important conclusions from it. Conclusion number 1, work done by a constant force from A to B depends only on the positions of A and B and not on the actual path taken. We have already proved that particle has taken two different paths, but work done is same. Conclusion number 2. The work done by a constant force in a round trip is 0. That is, if a particle goes from A to B and then comes back to A, then net work done is 0. So in this example, if work done from A to B is mgh, then work done from B to A will be minus mgh. So net work done is 0. Scenario 2, when force is variable. Suppose force F is acting on a particle and it is getting displaced from position xi to xf. Force in terms of its displacement x is given by the formula Fx is equal to ax plus b Newton. We have to calculate the total work done by this force. So total work done W is equal to integration of Fx dx from xi to xf. In place of Fx, we will put ax plus b. So W is equal to integration of ax plus b dx from xi to xf. That comes out to be equal to A by 2 into xf square minus xi square plus B into xf minus xi. Suppose force displacement graph is given and we have to calculate the work done between x is equal to 0 to x is equal to 4 and between x is equal to 0 to x is equal to 5. Work done W is equal to integration of fx dx from xi to xf. Integration of fx dx is area enclosed between the curve and the x-axis. So work done between x is equal to 0 to x is equal to 4 will be area of this trapezium. We can divide this trapezium into one rectangle and one triangle. So work done in this case will be 30 joule. To calculate the work done between x is equal to 0 to x is equal to 5, we need to add the area of this trapezium and this triangle. Work done corresponding to this triangle will be negative as force is minus 6 Newton. So work done corresponding to this triangle will be minus 3 joule. So total work done between x is equal to 0 to x is equal to 5 will be 30 joule minus 3 joule, and that is 27 joule. Scenario 3. When force and velocity are perpendicular to each other. We know that work done W is equal to integration of F dot dr. In place of dr, we can write v dt as velocity v is equal to rate of change of displacement. So work done W is equal to integration of F dot v dt, and that is equal to 0. Since force and velocity vectors are perpendicular to each other, so their dot product will be 0. So work done in this scenario is 0. Scenario 4. Work done by a spring force. Consider a block is kept on a smooth table. It is connected with a light spring whose other end is attached to a wall. This spring block system is in equilibrium. Suppose the block is at x is equal to 0. Now a horizontal force F is applied on the block so that the spring is elongated. Let's say block is at x is equal to x1 now. Since the spring is elongated in forward direction, so force on the spring will work in opposite direction as per Hooke's law, and it is given by F is equal to minus kx. So work done by the spring force will be equal to integration of F dot dr. F is equal to minus kx. So W is equal to integration of minus kx dx from x is equal to 0 to x is equal to x1. Minus k is constant, so it can be taken out. So W is equal to minus k into integration of x dx from x is equal to 0 to x is equal to x1. So W comes out to be equal to minus 1 by 2k x1 square. Now consider the block moves from x is equal to x1 to x is equal to x2. So limits of integration will be x1 to x2. So W comes out to be 1 by 2k x1 square minus x2 square. You need to remember this formula. In figure 1, spring block system is in equilibrium. Let's say block is at x is equal to 0. This is our reference line. Movement of block and spring towards the right side of reference line will be considered positive and towards the left side will be considered negative. In this figure, block is pushed towards the wall so that spring is compressed. In third figure, block is pulled away from the wall so that spring is elongated. In this table, we have calculated the work done by a spring force in different cases of initial and final states of the spring. For example, in case 1, initial state of the spring is natural. So x1 is equal to 0 and final state of the spring is compressed. So x2 is equal to minus x. Putting the values of x1 and x2 in this formula, W is equal to minus 1 by 2 kx square. Similarly, we can calculate the work done in different cases. In next video, we will talk about potential energy. If you have a question, you can ask me on my Discord server. If you have not subscribed my channel yet, please do so.